స్టార్ట్ చేశాను. వస్తుందా? థ్యాంక్ యూ. ఐల్ స్టార్ట్. ఓకే. Hello, good morning. I can't see myself live, but I've been told that I'm online. So let's start. Good morning after a long gap. I'm sorry I missed your last week's my slot. I was called into a meeting. In any case, I'm not very comfortable with continuing with histology simply because you all haven't seen the slides under a microscope. Now I can describe the visual to you in great detail and give you all the theoretical points, but it's not going to be the same as actually seeing the slide. And now with all the educational institutions in Telangana state being indefinitely closed with the second wave, we're trying to figure out better ways to bring you a practical experience online, but we haven't arrived at any great solutions yet. Just give us a little more time. Also, we're busy with your senior. Their final exam has started. So just coast along with us. Keep in touch with your books. Take a notebook and write down where all your doubts are. Some of you are asking me doubts on your chat group. I'm happy to answer that, though I may not do it immediately. I'll be available. But till then, today let me finish the remaining two basic intrinsic types of tissue, so that general histology curriculum as far as theory classes are concerned will be over. Then we'll have to do a catch-up practical for you as soon as you hit campus. Alright, so let me just check if I'm beaming at all. What I've noticed as looking at the earlier classes, the classes we are taking from the medical college campus, there's a lot of echo because of the gap between the speaker and the microphone of the system. So I'm live. Goody. Alright, there are only about 61 of you, but let's do it anyway. Okay, so back to my PowerPoint. So far we had covered the two primary basic types of tissue called epithelial tissue and connective tissue, and all their subcategories, and we discussed on the basis of what parameters or factors do we make this classification, and how does it serve the purpose of understanding histology better, particularly from the functional point of view, because tomorrow, next year, that will be the basis of your understanding of disease process or pathology itself. So the third type of tissue we look at, which is considered a primary type, is muscle. We already said muscles could be big huge ones which you see, which you build up in the gym, or really tiny, just a few slivers of spindle shaped cells, such as those which serve your autonomic functions inside your viscera, like around the pupil of your eye or in your fingertips. Okay, that's not viscera, that's skeletal muscle, but let's say phonation muscles, your vocalis, which vibrates for producing voice. So there are a whole bunch of muscles. But the common characteristics for all of them is that a cell, which we call a muscle cell or a myocyte, by its intrinsic nature, it can contract or shorten its long length with force, so that if it is attached to anything on either side, it can exert that force on that item, on that thing. When they all act in coordinated concert, they can move the entire body. And when they act within an autonomous function of your circulatory system, they can pump blood in a very preset, orchestrated, extraordinarily sophisticated, synchronized way. The types of muscles we have are skeletal, striated, which means that when you look at it in a certain way, under a certain stain, this muscle cell itself looks striped, as if it's got stripes, like black and white stripes. Only in this case, even in electron microscope, it looks like black, white and grey. In a stained slide, which you will see under the microscope, under high power only, it will look like purple and pink stripes. And in terms of function, they are of a voluntary nature, which means the kind of nerve supply they have is under your voluntary control. Cardiac muscle is also striated, but it is involuntary. In looks, it looks like it has the same stripes, but it is slightly different. And in function or in control, it is of an involuntary nature, which means its nerve supply, its neuromuscular junctions are different. They are not under control of your conscious brain, but only of your subconscious or unconscious brain. Smooth muscle is entirely involuntary, and in look, that means when you look at it under the microscope, or rather in its appearance, it is non-striated, which means it doesn't have these cross striations, which are very significant in the other two types of muscle. Skeletal muscle, the bottom of the figure, this purple one, is what it will look like at 800 magnification. We never show you that. Maximum we'll show you is 400. But what you're supposed to recognize it as is 100. So imagine it is only 1/8 of this magnification. So each of the cells will be this narrow. And the cross striations won't be so bright. They'll be just like very, very, very fine cross striations. We draw this in this magnification for you to understand what is going on. So if you have a singular myocyte, a long cylindrical cell, this is what it looks like, right? And in it, or rather on it, at the periphery, on the outside of it, nearly on the outside, just under the myolemma, that is the cytoplasmic membrane of the myocyte, you have a nucleus which has become flattened and plastered and pushed, because the cytoplasm is full of these fibrils which are giving this cross striation appearance. So this stripes look is happening because of the thickness and the density and the in tandem or organization of myofibrils in that cell, in each cell. Now, any one cell normally in the body is never so long, but in muscle cell, several cells have actually fused to form a singular syncytial fiber. So a fiber in this case is not a naked eye fiber that you see, but we call it, the name has stuck. We use the word fiber. What we mean is a singular skeletal muscle cell situation, syncytial cell, which shows peripheral flattened nuclei and cross striations within the cytoplasm. These 2 points are the diagnostic points: nucleus near the periphery and cross striations. The correct word is cross striations because the striations are at right angles or perpendicular to the long axis of the cell. That is the main point to remember. All skeletal muscle, all kinds of muscle, will have longitudinal fibers actually. The actual fibrils, myofibrils, actin, myosin, etc., are along the long axis of the cell. The arrangement is longitudinal, but they have certain zones of overlap, and what you see out of focus. You're not seeing each and every actin myosin fibril. You're seeing all of them together, where actin and myosin overlap each other for a short distance only. And so there's a gap when there is no overlap, and then there's another area where there is overlap. So the overlapped area will give a certain color or a certain reflection to your eye, and the non-overlapped area will give a lighter reflection to the eye. So you have dark light zones. That is the cross-striated appearance. There are actually no striations. There's nothing vertical, linear in the perpendicular axis of that cell. Nothing. All the structures are linear along the longitudinal axis of the cell. But the appearance to your eye in a stained specimen at a certain magnification is that their overlap, non-overlap areas are so perfectly orchestrated that they look like straight lines or cross striations. Each cross striation actually consists of like 20-30,000 myofibril zones, all exactly in line with each other. If they were to move out of line with each other, even by like 1 nanometer or something, you won't see the cross striation. They won't be so clear. But they look like lines or stripes because they're so much in tandem. The zones of overlap of every bunch of actin myosin are in line with each other, which gives the effect of a beautifully orchestrated coordination, making the contraction of the cell very efficient. You get the maximum movement for the minimum ATP spent. Marvelous machine, right? These are your natural biological motors, right? They generate action with a little bit of energy spent, right? A motor will have a piston moving or something, in engineering or in physics. These are the motors which run our contractile action within the body and for the body as a whole. So these cross striations are the appearance of the exactly aligned overlap zones of the actin myosin interactions. You've learned all this in physiology. They do it in exquisite detail. But how it looks under a microscope, if you were to take a small biopsy of your patient's muscle because they're having some issue, some motor issue, some complaint of weakness or inability or incoordination, and you want to diagnose what might be the problem inside the muscle cell which is creating this effect for my patient, then you might take a muscle biopsy, especially if it looks like a bump or a lump which might be a tumor. Then the internal architecture of your muscle may have gone so badly disarrayed that it might be visible in a stained slide. So there will be indications when you will be called upon to ask for a muscle biopsy, and then you will be able to see how this beautiful, perfectly geometric arrangement has been disturbed, what misalignment has taken place, and that will give you a clue to what might be the basis of the disease. What disease does this person have, and that will allow you to take a decision on how to manage it. So therefore, knowing the healthy, perfect arrangement for each type of muscle is very, very important. It has to set in your visual memory as well as your verbal memory. You have to know all the terminology, what is called what, why it is called that, where is it, right? As far as a normal, healthy adult muscle cell of skeletal muscle type is concerned. Cardiac muscle is also very, very similar looking cells. So each cardiac myocyte is also a long cylindrical syncytial cell. It has two extra features. One is that the cells can branch. The cell can have, instead of being one single long cylinder, it can have a little branch kind of cylindrical extension, which will go and form a cell junction with the next one somewhere, So where the cell junctions are formed, you'll see band-like structures which are called intercalated discs, because they are very specialized cell junctions between these striped cells. That means cross-striated muscle cells. Only muscle cells do this, have this kind of cell junction, and only cardiac muscle cell has this special junction which is between one of the branches of its cardiac myocyte and another branch from another cardiac myocyte, usually, which will join up. So actually, if you come to see, let me see. Okay, so this is one cell junction, right? And this is one cell junction, and this one, and this one. So the actual shape of this cardiac myocyte is one longish thing and another longish thing and one branching thing in between. So actually the shape of my cardiac one myocyte is a Z, cylindrical Z. And it is served, at least in this picture, by only one nucleus, but usually it has lots of nuclei. They're very high energy cells and high metabolism cells. So they may actually, they may end up having more number of nuclei per unit length of muscle. Let's see, if you go for skeletal, no, actually both are expending great amount of energy, so they're comparable. So the common point with skeletal muscle is the peripheral flattened oval shaped nucleus, right? But you can see the nucleus here is not looking so very, I'm sorry, this is looking central. But this diagram is not looking very central. I'm sorry, here they made it opaque. Okay, this is a painting. This one is a painting. This is an actual photomicrograph. In the painting, they put the nucleus as if it's on outside of the fiber. It's not actually. It's inside. A nucleus has to be inside the cell. But okay, it's kind of like bulging the cytoplasmic membrane outside. The visual mistake of mine. Sorry. So the point here is that the nucleus is inside, but it is pushed to the periphery. It is oval and flattened. So when you look at it in section, it looks like a dash, right? You don't see the whole ovalness of it. You look at it as if it's in a cut section of a nucleus. And what dominates is the cross striations within the cytoplasm. Whereas in a cardiac muscle, if you were to see it in this painting, you could interpret it as central or peripheral. I'm not even very sure how they do this. I think the point they are trying to make is they made the nucleus overlapped by the stripes, which means it is in the center of the cytoplasm and the cross striations are around it, which is exactly the fact. So you have a cylindrical myocyte, and somewhere in the middle of it, the cytoplasm has made a gap, a space for the nucleus to occupy. So the nucleus is looking like it's in between the cytoplasm, and you'll have cross striations on either side of it. Can you see cross striations here? Really nice, very fine parallel lines. Dark purple, light purple, dark purple, light purple, right? So these cross striations get disturbed in some place where the nucleus is occupying, and around that there's a little bit more bare cytoplasm available. Other organelles will be there, Golgi apparatus and vacuoles and whatever other things will be there. So in cardiac muscle, the center of the cytoplasm is not as well packed with actin myosin filaments as skeletal muscle. In skeletal muscle, it is so packed that you can't see any other organelles, and the nucleus which is necessary is pushed to the side. Whereas in a cardiac myocyte, there is a nucleus which is centrally placed. There are cross striations because the myofibril component is definitely in tandem with each other. The alignment is extremely good, but they are not all completely continuous because they have to make a place for the nucleus and other things, which is seen in a stained specimen. So this is also 800x magnification, and you're seeing that in the center of the cytoplasm there is a space for a nucleus which is looking kind of oval. It's actually looking a little funny shape. Normally you get to see kind of ovoid nucleus, right? And in between, if you follow any one length of if you follow one whole band of cross section, suddenly you'll come across a much darker line, purple like a line, which is across the width of that muscle fiber, and these are called intercalated discs, which are the special junctions between contiguous cardiac myocytes. So this is a specialized junction which allows for very rapid transmission of impulse from one cardiac myocyte to another. Now you've already learned in neuromuscular junction that the most peripheral part of a nerve fiber, incoming nerve fiber, motor fiber, will spread out into foot plates and end on the myolemma, on the surface membrane of the muscle membrane, right? And each of those neuromuscular junctions, there will be a release of the neurotransmitter, which will depolarize the surface of the membrane and give the contract order, then this whole thing will contract. So when it does it to any one cardiac myocyte, the intercalated disc specialized junction allows that impulse to also pass to adjacent cardiac muscle. This is something which smooth muscle also does, that through the intercellular junctions, the wave of depolarization is able to be conducted across the intercellular junctions. So smooth and cardiac muscle have this common property. Cardiac muscle actually shows the intercellular junction in a more dominant way. In a normal H&E staining, you get to see the intercellular junctions very well at a right angle to the long axis of the fiber. In smooth muscle, I'll show you in the next slide, all the cells are spindle shaped, they're not cylinders, and the spindles adjacent to each other will have intercellular junctions, but they're not, you can't see them as very clear or special or separate stained areas. In cardiac muscle they are, and they look like they're at right angle junctions because it is a branched cylindrical cell which is meeting up with another cell. So cylinder to cylinder there is one junction, right? So a cylindrical cell finished, another cylindrical cell started, and there is a junction. So the cylinder to cylinder meeting is happening at right angles to the long axis of both the cylinders. That's why it becomes visible. That intercellular junction becomes visible, and we name it and we label it, and we use it as a diagnostic point for what kind of muscle this is. So first point, if you're just generally looking at everything like this all together, they seem to be cylindrical cells, cylindrical shaped cells. You can clearly see cross striations. Automatically only muscle shows cross striations. No other tissue in the body shows cross striations. So automatically you will rule out everything else and you'll say this is muscle. Now the only two types of muscle which have cross striations are cardiac and skeletal. So which one could this be? Now this nucleus is looking central and you're seeing intercalated discs. So it can't be skeletal muscle, it must be cardiac muscle. That's how you narrow it. Alright. Smooth muscle is longitudinal cells, but not cylinders, they are spindle shaped. Right? They have tapering edges. Right? The edge is narrow, the center is fat, wide, and in that is the nucleus. So long spindle shaped cells with central oval nuclei, right? Not peripherally placed. And no matter how much you look at them, you won't see any cross striations. Not that they don't have myofibrils. The actin myosin is very much there. After all, they also have to contract. But their alignment isn't so perfect. So one dark zone and another dark zone are not exactly perfectly in line with each other. So when they refract to your eye, they do not give the appearance of straight lines. Right? They are there. They're very much there. But they're not so well aligned, first point. Secondly, they're not so dense per square nanometer. There aren't so many fibrils packed so tightly within a smooth muscle cytoplasm. Number of myofibrils are less. Their alignment with each other is not so perfect. Therefore, cross striations do not appear in smooth muscle. That is the logic, or that is the understanding of it. So you're seeing spindle-shaped cells, you're seeing central oval nuclei. You're not seeing intercalated disc, you're not seeing cross striations. This is smooth muscle. Okay, again, this is 800X under low power. It will be just like pink long lines with little purple dashes in between. If you look at it carefully, you'll see that the purple dashes are in the center of the pink. They're central nuclei. So once you see central nuclei and spindle shaped cells, you're thinking muscle. Since there are no cross striations, it's not skeletal, it's not cardiac, it must be smooth muscle. The other kind of tissue, I think I'll finish with it because we only actually show you 2 or 3 slides in practicals. And if you remember, we did we already classified when we talked about nervous system. We said there are nerve cells, and I think I took one general introduction to histology class. We said there are neurons and there are neuroglia. They are all together found in brain, spinal cord, and all the nerves that you have. Their unique property to be called nervous tissue, they produce action potentials, not glia. actually. But yes, they support the neurons which produce the action potentials. Consists of a lot of cells, that is neurons, which have the typical cellular characteristics of a cell body or soma. Incoming cell processes called dendrites and outgoing cell processes called axons. Actually, whether it's incoming or outgoing, you can't tell from looking at the tissue, but basically a soma with a whole bunch of cell processes. It could be 2 or 3 or several. When it is 2, we call it a bipolar neuron. But the dominant pattern in the body is a multipolar neuron. Unipolar, we don't even have in the human species. We have pseudo-unipolar neurons in certain ganglia. The other kind of cell, which is which is like 100 times of neurons, is the neuroglia or support cells. So neurons are, this is the diagram. This is our understanding of what it looks like. You've done this 100 times in your biology so far, but this is what the stained slide looks like, and this is at 240x. So in a low power magnification, you are seeing a single neuron. They are large cells compared to the average size. If you see all the cells in the body, all the generic types of cells in the body, they tend to be around 10 microns, 7 to 12, 7 to 15 microns, not bigger than that. Bigger than 10, 12 is considered a big cell. So a neuron is a big cell, but the soma is big. And plus, if you put all its processes together, it's a very, very, very big surface area cell. I mean, its neurolemma, its neuroplasmic membrane is huge in terms of the amount of area it covers. And out of these, majority of cell processes will be dendrites, and one somewhere, dominant one, will be an axon, and it will be identified by a little bare area where it starts, where no organelles will be visible. Now this could also be an axon in terms of its thickness, but if you look at its base, if it's showing organelles, then it's not an axon, it's probably a dendrite, right? So you have to look at it under a very good stain and good magnification to figure out which one is the axon. That may not even be so necessary when you're looking at a slide of nervous tissue. Firstly, to get a nervous tissue biopsy, I mean, you don't want to go take a pinch of somebody's brain or spinal cord just like that without sufficient reason, right? There has to be some really serious reason to ask for a nervous tissue biopsy, right? Because that bit of tissue loss will also cause some dysfunction for your patient. So unless you really think that's a tumor, or it is a degenerative disease, or it is something where the diagnosis is hanging on what is the cellular configuration or arrangement or disarrangement, only then we will ask for a nerve biopsy. If we do that, and if we stain it, and if we see a mistake in the arrangement or a disturbed arrangement, a cell soma or dendrites or axon not looking quite right, then we might come to some conclusions about the disease. So you have to be able to recognize, first of all, that there is something called a cell body and a thousand processes happening there. Not all of them will stain. HNE is not the best stain to have for nervous tissue. In fact, a lot of special stains were developed by some very brilliant neuroscientists to be able to see nerves at all in the first place under a microscope, because it doesn't lend itself to HE very well, but it does to some extent, and that some extent has allowed us to delineate the neuronal shape, size, configuration, architecture to some extent, and we are able to make out that they're very large cells, they have these cellular processes, and they're dominantly surrounded by a whole bunch of much smaller cells, which are called neuroglia, which you only get to see the nuclei. You only see little dots, dashes of small nuclei surrounding the neuron, whereas the nucleus of the neuron itself is usually a large ovoid structure, where the nucleolus is also usually very clearly visible. The nucleus with nucleolus is a strong characteristic to identify as a neuron. Even if you don't see the processes, you see something oval and you see a nucleus with a nucleolus well visible, large nucleus, you might be thinking of neuron. even if you can't see the processes. But usually we do see the processes, and this one is a multipolar neuron. So in this, again, it's being called unipolar, but you can see the process is immediately dividing into a incoming and an outgoing. So it's a pseudo unipolar neuron. This location is within a ganglion, which is an aggregation of neuronal cell bodies outside of the CNS, right? So you have paravertebral ganglia, you have parasympathetic ganglia in your head and neck, in your abdomen, so many places, and you have the ganglia related to the roots of your spinal nerves. We'll come into each of that. So in the practical, we will show you neuronal cells in general histology. We will show you sympathetic and autonomic and paraspinal ganglia, two different types, to show you that the cell bodies are now seen in section, right? You're not seeing the processes incoming or outgoing or anything, and you're seeing that every one neuronal cell is surrounded by like an envelope of dash-shaped glial nuclei, which are called satellite cells. So the nuclei of the neuroglia, which are wrapping up closely around the neuronal cell body, are together called satellite cells. So the appearance of a large pale staining cell body with a large nucleus with nucleolus clearly visible is indicative that these must be neuronal cells. When you're seeing a bunch of satellite cells around each one of them, then it is more in favor of neuronal cells. Now in this particular slide, you're seeing they are of different sizes. There's a big one and this is a small one. There's a big one and these are small ones. These are likely to be autonomic neurons in an autonomic ganglion, right? But if they are all of the same size, more or less the same size, then they are likely to be a paraspinal ganglion. So we will look at two different types of ganglia and we will differentiate them when you see them side by side under the microscope. What here you have to remember is this is how a bunch of neurons will look when they are seen together as part of a ganglion. Alright? Okay, same thing. Big sized ones are neurons. Funny looking shapes. The soma has all kinds, because it depends on, it's a network like, so three-dimensional structure. You could cut it like this or like this or like that. So depending on which way it's got sliced in your slide. Your slide is after all a slice through the tissue. You'll get different shapes looking neuronal cell bodies. But you will definitely get one or two which look like the star-shaped thing, with these extensions. So that's typically a neuron with a neuronal nucleus. Right? Even in the small ones, you'll see the nuclei are pretty clear. Now, sometimes the slice won't go through the nucleus. So if it doesn't show a nucleus, it doesn't mean it's dead. It means my slide section didn't go through the nucleus. So this one looks like it's just Kali. It's not like that. The slice didn't go through. So you look at least 10-20 neuroglial soma, and you will see at least 4 or 5 nice big round oval nuclei with nucleoli, and then you know that it is a neuron. And this slide was supposed to show you neuroglia, so all the others, the remaining are all glia. If I remember, I asked this question when the last time I talked about CNS classification or something, that the homework was what are the different types of glial cells. I don't know how many of you did the homework. If you didn't do it now. There are oligodendrocytes and astrocytes, and astrocytes are again of two types. So that we can't differentiate. Even at 240x, we can't differentiate in a HE stained slide. You need special stains for that. At undergraduate level, you don't need that. But anything which is not of neuron size is a glial cell. And you see in one little field, you're seeing what? 1, 2, 3, 4, 5, 6, 7 neuronal cell bodies, but you're seeing 60 or 70 glia. And this is even when the majority of cells did not take up the stain, which means maybe 10% of all available cells have taken up the stain. Out of that, 1% is neurons and 9% is glial cells. That is the density, that is a proportion within nervous tissue. Right? The supporting cells which help in the nourishment, which help in the insulation of one neuronal impulse from another neuronal impulse. Both very, very important functions are being performed by the glial cells. So the point is to be able to differentiate neurons from neuroglia and within neurons, which part of the neuron you're looking at, and whether later when you see it under the slides, whether this might be from, let's say, cerebrum or cerebellum or ganglion. Slight differences in characteristics of the neuronal cell body itself will indicate you where this piece of nervous tissue might have been taken from. We will confirm that and repeat it and affirm it for you when you come for the practicals. So I will stop now. It's been a short class. As far as I'm concerned, general histology slides have been covered, though I haven't shown you the best possible pictures. Ideally, it should show you straight from the microscope. The camera attachment should be on the microscope, the real slide, and I should be able to feed it, but I couldn't do that with my laptop or even in the department. We'll see. If you guys are not returning to campus in a hurry, then I will do it like I'll create a kind of a slideshow in a revision class, so that from the curriculum point of view, your practice are also supposed to be covered. And we'll do a revision live when you are there on campus. And when you come, you'll have to be prepared to do a lot of intense work in a short burst of time. Get the theory right. Get the theory strongly embedded in your brain, so that when the practical happens, it'll be easy for you. Okay? So bye for today, and I'll see you again next week.